as you all correctly voted, those of you voted for right, this thing is going to be a bigger number than just this square, than this value itself alone, the absolute value of that alone. Because if we ask what is the speed of the drop ball, it's just this part. This is equal to 0 for the drop ball, right? There's no horizontal velocity component. So you take the square to the square, that's the same thing as the absolute value. Just the absolute value of the, right? Great. So the shot ball has this speed, we can calculate it. All right, we worked it all out. And we did it by the numbers. We pedantically went through, we wrote down x and y equations for all objects in the problem and solved for t and then we solved for v and so on. But there's a basic intuition for what's going on, right? What's going on is that the equations of motion in the vertical direction are the same for the two balls. So if we took a strobe light or if we just took a camera and took pictures at different moments in time of these two balls, right? What we find is that one snapshot, they'd both be at the top. Next snapshot, this guy's fallen a little bit, and he's moved quite a bit out to the side, but he's only fallen by the exact same amount, right? And if we wait the same length of time later, he's fallen much further. In fact, it'll be 4 times as far, right? He'll be all the way down to here. If we wait that same length of time again, because after all, the amount of distance you travel, where's my equation? The amount of distance you travel, right? From, if this is equal to 0, if you have no initial velocity, right? The amount of distance you travel is just equal to something that goes like a times t squared. So if you look for, at a time that's twice as long as the first time you look, well, 2 squared is 4, you're 4 times as far along as you were. The distance, x, or in this case y, is 4 times bigger than it was the first time. So that's 1 unit of time, you've gone that far, and then 1 more unit of time, you've gone 4 times as far. But the same is true of the other ball. So if you took snapshots, no matter what time you did it, right, you'd find that the two balls have the same height. And that's how it is that, like when I set this problem, I didn't tell you exactly how tall this was. Yeah, it's about a meter, maybe it's a little more, a little less, but it didn't matter. When we solved these equations, we did it all symbolically. I didn't actually ever plug any numbers in here. The answer that it hits at the same time, the two balls hit at the same time, it doesn't depend on how tall this thing is. All that matters is that the two balls start at the same height, whatever that height is. Why is that? Because the equations of motion are identical. So it doesn't matter how much time you wait in the future or how far it travels, as long as it's the same distance, they hit at the same time. And this is the intuition why, right? This is what it looked like. All right, so I think it's a really instructive problem. Here's one that's kind of similar, but it sort of flips things on its side. So in this problem, instead of both balls moving vertically, I've got a cart and a ball. So I've got a ball inside a cart, and I can arm it, push it down like that, and I can turn it on. Let's see if I can turn it on. Is it on? Ah, I think it's on. And there's a fancy contraption back here that is triggered whenever it passes by this little stick, and there's a little thing that sticks out and breaks a little beam of light. And when that happens, a spring shoots the ball straight up. Okay? And the question is, all right, well, if this is a frictionless surface, and it's very close to frictionless, if I start this thing going, oh, it's slowing down a little bit, but not too much. It should go at a constant speed, this cart. And when it goes through here, what happens here? I'll shoot the ball straight up. So I'll just shoot it and see what happens. Go straight up, and comes right down. So the idea is, I have one of these at home. It's a lot of fun. So I have this thing moving along at a constant speed, right? And it goes past this guy, and what'll happen is the ball comes shooting straight up. Now, the ball is going to have some horizontal component to its velocity too, though, right? Because it's moving along with the cart when it gets sprung straight up. So when I start right here, you saw me straight up in the air. That's because the cart wasn't moving. But the cart's moving when that happens. The ball acquires both a little bit of horizontal velocity and some initial upward velocity, and then it goes through some parabolic trajectory, right? So I'll have you vote again. First of all, who has seen this demo before? Lots of you have seen it. Not like 10 of you have seen it. So you people don't vote. For the rest of you, you can vote if you want. When the thing's moving along, I'm not going to touch it. I'm just going to let it go and have it go at constant speed as it moves along. Will the ball land ahead of, behind, or inside the cart? So who would guess that the ball's going to land ahead of the cart? Nobody. No takers. We should bet real money. All right. What if I do this and who thinks it's going to fall behind the cart? How many people think behind the cart? So who thinks it's going to land just dead center right inside the cart? Yeah, and many of you aren't voting. Half of you are, at least half of you are not voting. I think the ones you seen before did vote in the cart, and I think that's right. So let's see what happens. See if it works. All right. So it moves along. Oh. I can't break this thing. All right. Oh, wow, it's stuck. Is it a magnet? Oh, it's got a magnet. Yeah, so, off the rails. Yeah, and that's right. So it did land in the cart. It wasn't perfect. Let's try it again, see if it's better this time. I'm going to go a little faster, too. Yeah, I was right. That was dead center time. No, it wasn't the first time. So good, it does land in the cart. And why is that? Well, the same intuition we used over here works for this problem. This isn't too bad. You can still think about it pretty simply, right? The idea is that you've got a cart, right? It's moving along. At time 0, the ball is ejected, right? The ball follows a parabolic trajectory, and the question is, okay, well, does it land in the cart? Well, we can go through the same exercise, right? We can write down for the cart, and then we've got our x direction of motion, and we say, the x direction, and what are my axes? Let's define them this way, the same way as we did last time. X and y. First thing I do is I label my axes. Here's my origin, and let's choose the origin to be right at the point where right here, right at the point where the ball shoots up in the air. And we can go through the same exercise, right? We can do the x direction of motion and the y direction of motion for the cart. X of cart equals x of cart initial, right? Which is 0, because we chose our axes to make this simple. And then we add, what is it? We add v times v initial of the cart. In the x direction, lots of subscripts, times t, right? And then we add 1/2 a of the cart in the x direction, times t squared. What is a of the cart in the x direction? Yeah, the x component of the acceleration is 0. In fact, that's true for the cart and the ball, isn't it? So the only thing that survives over here is this. So we say, the cart's position along x is just going to be its initial velocity. Let's again say, let's call this thing v. Let's say v is the initial velocity of the cart in the x direction, right? So it's just equal to capital V, right? The thing we're given times t. That's it, right? What about the y direction for the cart? If the cart has 0, we find our axes so that the y value of the cart is 0 to start with. Does it ever change for the cart? It's always equal to 0. So y of cart equals 0. Very simple, right? Now we can do the same thing for the ball. Well, the x-axis of the ball is going to turn out to be exactly the same as it is for the cart. Like, that's the intuition for why it lands in the cart, right? In other words, x of the ball equals x of the ball initial plus v in the x direction initial for the ball. You notice I'm switching the order of these subscripts, but I don't mean anything different by that. I just want to make sure that all the ones I want to be there are there. 0 means times 0, x means x direction, v is ball, times t, plus 1/2 a acceleration. Now I want the x component for the ball times t squared. Yeah, but that's equal to 0, right? You guys all told me that, you're right. The ball's in the air, it is accelerating. The ball's accelerating even though the cart's not. But the acceleration of the ball is only in the vertical direction, only in what we call the y direction. So that's 0. This is also 0, for the same reason it was in the last guy. We chose our origin to be right there. So we know we get the same equation for the ball's x position, right? Times t. Does everyone agree? And what we get is exactly the same equation of motion for the x direction for the ball and the cart. We can stop here. We don't have to calculate the y. I mean, we could. We can calculate it. Maybe ask some question that requires it. But for the question of does it land in the cart or not, we're done. Because the fact that these are the same equations of motion tells us that, again, we got our camera and took photographs at different times during the evolution of this thing. What we see? We see that at this moment in time, the ball's right there. At this moment in time, the ball's going to do this, right? At this moment in time, the ball's up here, and the cart's right here. At this moment in time, the ball's right here, right? And so on. So that no matter what time, like we didn't even calculate, we did not calculate what time the ball lands back in the cart. To do that, we'd have to go through, we have to have the y equation of motion for the ball and then relate these things. We're going to do that in a minute with a different demo. But if all we want to know is does the ball land in the cart or not, the answer is yes, and it's yes because at any moment in time, the x the x value, right, which is 0 on the x-axis, the x value of the ball and the cart are always the same. So that means that no matter what's going on up here, it's going to have to, when it comes back down, it has to land in the same place it started on inside the cart, right? Great. So there's the same intuition, just that this time there's vertical lines instead of horizontal lines we had here. So some of you have seen these things. Let's try a more challenging question. What if I put this thing on a slope? So where's, oh, do I have a block? Oh, I may not. Oh, here we go. All right. What if I do this? Don't tell the demo guy. Set this up. What if I put it on a slope? So to actually go through the math and solve the physics on this requires some information that you don't know yet. I haven't told you. So last time I asserted that if you have a slope, that you have a constant acceleration situation, just as you do when you throw a ball in the air, right? But I didn't actually prove it to you by measuring. And I made a comment, and the comment's true, but I made it misinterpreted. I said, oh, you have to take my word for it. Well, you don't take my word for anything, right? And we can measure whether or not it's true. And let's do a really quick and dirty measurement and see if it looks like it's true, that this is constant acceleration. So the way I'm going to do it is I'm going to try to count off 2 seconds. Well, first 1 second and then 2 seconds, and see whether or not the cart, when starting from rest, travels 4 times as far, right? That's what we found made sense over here, right? When we have this equation. Here it is. This t squared dependence of the distance as a function of time, right? We can use that to see whether or not it's plausible this is constant acceleration. It is, but let's just see. And I got to be careful I do this in such a way that I don't actually break it. Is there a yardstick up here? Or it's probably a meter stick, isn't it? Here's a stick. All right. So here's what I'm going to do. I know this is so Rube Goldberg, but all right. Guys, you know what that is about. So let's count off. Oh, is there a ball here? I don't need the ball to shoot. Oh, let's not do the thing out with the ball. Okay, it won't shoot that. Okay, so we're just going to count off 1 second, and then we'll do 2 seconds and see if it goes 4 times as far. I'm starting from right there. So go. 1. All right. So how far you got about here? Went from about here to here. Does everyone see that? Let's try 2 seconds now. Well, such dexterity is needed. All right. So we'll say go. 1, 2. All right. So I think I did that fairly. I think I got about this far, and that is about 4 times as far. There you're going. No. Did I count them off badly? Did I go too early or too late? Too late. So you think I cheated? Oh, all right. All right, let's do this. That's okay. I think it's more fun for you guys to watch me struggle. All right, so let's see if I can do this fairly if you guys are happy with it. The real trick is it moves too fast already. Maybe what I should do is make it on a lower, here. This is steep enough that it's actually speeding up faster than I would like, so let's do that. Let's make our life a little simpler. So this will be, so making it lower, incline should make it lower acceleration. And in fact, that's true. I'll show you next week, or maybe on Thursday, but certainly next week, we'll calculate this explicitly from Newton's laws and force of gravity and the rest of it. Right now, we're just making empirical measurement. So we'll say, all right, I'm going to count 1, 2, 3, 4, 0, 1, 2. All right, so I think it was like 0 was about that, or 1 was about that far, and I think 2 was about that far. That's about right, qualitatively, within a factor of 2. You want to get away with that? All right. So I think that's, and that's about 4. I'm not cheating. It truly is constant acceleration. The main thing to get from this is that it's speeding up, right? And it's speeding up at a constant rate, so that every second goes by, it's going faster by whatever the acceleration is times that second, right? That's how much extra velocity is added on. Okay, so now let me ask you to vote then. What's going to happen? So now the cart is going down an incline. It's accelerating. We've established that, right? It's not going at constant speed anymore. But the ball's, up in the air. It's undergoing some acceleration due to gravity. So who's going to win? The ball's being angled. So now also notice the spring is angled now. So not only will the ball have some initial component of its velocity going that way, it's also going to be shot in a direction that's going to velocity that's pointing that way, right? Not straight up, a little bit of an angle. So who thinks the ball's going to land ahead of the cart? No takers. Wow. One person. Who thinks it's, two. Who thinks it's going to fall behind the cart, the ball? Oh, lots of people think it's going to fall behind the cart. All right. By lots, like a fifth of the class. Who thinks it's going to, who thinks it's going to land in the cart? So almost as many has thought it's going to fall. That's interesting. All right, good. This is a good demo because it's a good spread in answers. Who's confident about their answer? One person's confident. Two people are confident. So yeah, so if the money came out, the hands all go down, right? All right, well, let's see what happens. I'm going to try and do this again with the stick so that I can stay out of the way, not poke my eye out. Always important doing the demos. And I'll catch it down here. So let's see if it lands inside the cart or not. Yeah, dead center. Why is that? And it's true, the angles are the same, but there's a lot of things going on here, right? Both objects are accelerating. One's constrained to move in a straight line, one's doing projectile motion with a parabola. So let me ask you this. If I draw a picture of it, right? So here's the situation we have, right? Some angle theta. We didn't even measure what theta was. It's going to turn out not to matter. Put the question whether it falls in. So right angle. Oh, I don't know if this is a symbol for an angle. Like most of you know that. Just so it's clear what this little funny square is. What I mean by that is 90 degrees. These are perpendicular. Theta is some angle I haven't specified, but maybe the problem description says, oh, it's 20 degrees, or maybe whatever. Pi over 7 radians, or whatever it is, right? So here's the situation, right? The cart's accelerating down the hill. In fact, if these are equal time snapshots, it's bigger time. Actually, for equal, it'd be 4 times. We got to figure that out. 1, 2. I did back them up a little bit. So he went this far initially, and then that far after the next second, right? And there's some trajectory the ball takes in the air. Let me ask you this: so the ball follows the trajectory, but the cart that's shot is on some funny angle. So does that mean that the trajectory looks like this, where I've got a parabola with this as the axis, or does it mean that it comes out like this, where here's the axis? Does everyone see the difference? I've got a red parabola, a potential trajectory for the ball. There's a parabola where the axis of symmetry of the parabola is vertical. And then I've got a white trajectory that's around here where the axis of symmetry is at the angle given by this ramp. So which is correct, the red picture or the white picture? Who thinks white picture? Lots of you. Who thinks red picture? Roughly, actually, slightly more for the white. It turns out the red picture is the correct picture. Why is that? It's because once the ball leaves the cart, the only thing that's affecting it is gravity. The cart's out of the picture. I mean, it's in the picture, but it's not touching the ball anymore, right? The ball doesn't care anymore about what's sent in. It doesn't matter if it was a baseball bat or if somebody threw it or if it was shot out by this funny spring in this cart. It doesn't matter. Once the ball is in the air, it's undergoing projectile motion. Projectile motion near the surface of the earth, but the only thing that's acting on you is gravity. Always results in a parabolic trajectory where the axis of symmetry of the parabola is vertical because it's determined by the only thing that's affecting you, it's gravity, right? So that was useful because people voted, I think, mostly for the other curve. Most of you didn't vote, but of those of you who did, I think the white curve is more appealing. It sort of agrees with the symmetry of what's going on down here, right? But that's not what determines the motion of the ball. It's all the more surprising then maybe to you, like, why does it hit the cup? So the way to think about it is similar to the way we thought about these problems over here, but it's a more complicated problem. There's angles and there's multiple accelerations and all this stuff. Both objects are accelerating, and there's one piece of information I need to give you that you haven't been told yet, because to do it, we're going to do this when we get into forces. We're going to talk about what the accelerations are. Oh, someone left me a secret message here. What's this? Oh yeah, what does this say? C equals 300,000 kilometers a second. What is that? Speed of light. It's lickety split. Light is fast. That's for later. I'm not going to worry about that right now. All Okay, so how do we solve this problem? The way we solve it is we would write down, like, well, first of all, we've already established this is a constant acceleration problem. Both the cart is undergoing constant acceleration and the ball is undergoing constant acceleration. They're different accelerations, but they're both constant. That means we can use these equations to solve the problem and do the same stuff we did with the other problems. The only thing I haven't told you is how to calculate how great the acceleration is for an object on an incline. That's what I haven't told you. And so I'll just assert it today, but we'll learn why it's true next week. And the answer is that it's just the component of the acceleration of gravity that goes along the direction that the object is free to move along. And that kind of makes sense. If you have an object on an incline, it'll accelerate the gravity down that way. Not as great an acceleration we have if you dropped it straight, in air, right? And the amount is going to be proportional to the components of the acceleration vector along the slope. And we'll see why that is true due to physics. Newton's second law. We'll do all that either on Thursday next week. But real quick, let's see what that looks like. So here's the acceleration vector. Has magnitude g. But we only want the component that goes along here. How do we calculate that? Well, there's a couple of triangles I could draw that would help me do this. Here's one. So here's the g vector, right? Here's the this full strength, well, it should be full strength. Here's what the acceleration of gravity would be for a free-falling object. If it's constrained to move along here, here's the acceleration we'll get just along this incline. And is this angle right here? Right? So this line is perpendicular to that line, right? These are orthogonal, these two. And this is orthogonal to this. So that means that this little angle down here is equal to theta. It's the same angle as the angle over here. Very important to figure out how to relate the angles in these two triangles. You're going to be doing this all the time in this class. And the strict reason why that works is this guy's orthogonal to this guy, and this guy's orthogonal to that guy. So that means the angle between these is angle between these, right? I forget what you call that in trigonometry class, but there's a name for that rule. But it just sort of makes pictorial sense if you think about it. One thing I always do is a trick that I would advise you to follow. When I draw pictures of the physical situation and try to figure out what the components are and stuff, I make the angle here, I make one of the two angles much smaller than 45 degrees, and the other angle much bigger than 45 degrees. That way I can just eyeball it and see where the theta goes. In other words, if I've got a triangle like this, and I have theta labeled over here, and this is a much smaller angle than this one is, then I can just eyeball this and say, oh, that's a small angle, got to be theta. Without having to think through those, during a test, right, and I'm sitting there sweating almost stuff. It's a lot easier if I just draw my triangle so I've got an acute angle and make it really easy to tell them apart visually. The other thing to make sure of, though, is that the right angle goes on the opposite side of the triangle as the thing you're looking for, the vector that you're trying to break up into components. So this is the original vector, the acceleration vector. I'm looking for the component of acceleration along this direction. So it better be the case that these two components are smaller than the original vector, right? I can't get bigger components than the thing that they add up to. So a common mistake students make, though, is they draw a straight line here and then have some angle and make this a right angle, right? And if you do something like that, then you'll wind up with a component that is bigger than the original vector. It can't be right. So anyway, just be aware of that. Okay, great. So what is this up here? This is the amount of acceleration that the cart experiences down this incline. I'm asserting that. We'll see why later. Well, it's just g, the length of the hypotenuse, times what? Sine or cosine of theta? Sine. Opposite of hypotenuse. Am I right? Yeah, keep me honest. Easy to get that stuff backwards. And they think, yeah, that's right, because sine goes like this. Right, it starts out, so sine of small angles is like sine of theta goes like theta for small theta. That's how physicists would keep it straight. Oh, yeah, if it's a small angle here, that's a small side over there. Must be sine. Right? Good. Great. So then that means that we can write down our equations of motion, right? And and what are our axes? So I told you the choice of axes really makes a big difference. Let's do this. Let's make this our x-axis and make this our y-axis. So this is the first problem I think we're doing in this class. At least in the lecture, maybe we did this in discussion already, but where we've chosen axes that are not horizontal and vertical. And that might be disturbing to some students who aren't used to doing that, but it's really helpful. It'll make the equations easier to work with, I think, for this problem. It'll certainly be much easier in some cases. In this case, it's a little easier. In some cases, it's a lot easier. So what does it mean if I do that? It means that if I want to know what the equation of motion is for the cart, well, so for the cart, first of all, let's do the simplest equation that we have to think about. What is the y equation of motion for the cart? Well, y of cart equals y of cart initial. Well, we can go through this whole thing and write this equation out, but oh, now we should write it out. I'm making it. Yeah, all right, sorry. That wasn't the easiest equation. The easiest equation is the x equation for the ball, but that's fine. So let's write this out. It's y cart at time 0 plus what? Oh, yeah, the acceleration. Oh, yeah, well, let's see. I'll tell you what. Let's just focus on the one equation we really need. All right, two equations we need. What we really need to do is the same thing we did over here. In this case, all we had to do was show that the y, so in this case, the y of the ball and the two balls was the same at all moments in time. In this problem up here, all we really had to do, like I didn't bother to do the y equation for the ball. I said that as long as we know that the x equation for the cart and the x equation for the ball are the same at all times, then that'll tell us that it's going to land in the cart no matter what the y of the ball was doing. So we didn't even bother to calculate the y of the ball. So if I keep my head clear and look at my axes, which I should have done before I started blabbing on this, I'd say, well, what we really need to show is that, if it's true, that the x component of both objects is going to be the same at all times. And we don't know yet that it is, but let's check and see if it is. Okay, so let's do the x component for the cart. So the x component for the cart, well, x of cart equals x of cart. I'm doing the same equation we've done millions of times now. Plus, what is it? V x cart initial times t plus 1/2 a of the cart in the x direction times t squared. Well, let's define everything so that the initial value is 0. So let's put our origin right here where the cart starts. Okay. So that means that this thing's equal to 0. We don't know what the initial velocity is. Like the way I set this problem, I started it up here somewhere, and by the time I got down here, there was some velocity. And I didn't tell you what it was. I didn't say how far. But, so let's just give it a name. Let's say that this velocity along the x-axis, again, we use the same capital V we've been using for the other problems. Okay, so x cart equals whatever that initial velocity was times t, and it's growing positive with time, which makes sense. Notice I made my positive x-axis going downhill. Didn't have to do that, but that's a fine choice. So this is getting bigger with time. And now I add my 1/2. What is the acceleration in the x direction?